Sound test. Hello everybody. I will today talk about this educational round 144, which has just finished. I was going to first just maybe read some difficult problems before the stream. Then I realized that just after the contest ends I cannot submit things. So test. Oops, I have some echo here. Fixed. Then I realized I cannot submit just after it ends, so I thought maybe some of them I will submit, and eventually I was going to solve all of them and just submit things during the real contest, out of the standings of course. But I was stuck at E. I didn't think too much about F. I've tried E, I started coding something, but I couldn't solve it in like half an hour. So we'll see. Certainly I will discuss ABCD, and I don't know, there is a small chance that I will then just stop. We'll see. Most likely I'm like one observation, one sentence away from the solution. So what? Let's talk about update stream title. What's the stream title now? Yeah. This is Codeforces Educational 142 Division 2. Thank you. The bad thing on Twitch is that the old title will stay for the vote. I did the first problem as 1365. Nice, congrats. This is related to something we did yesterday during a stream. Let's start talking. First problem A, gaming forces. I have the codes, not always I want to show them. I guess, where's Genie? Oh, yeah. I close Genie just in case I start streaming before the competition ends. The code is easy, where I will discuss that in a moment. In problem A, you have some monsters with health points, like maybe 3 health points, 5, 7, 1, 2, 1. And you can kill some of them. Either you can in 1 second kill a monster, or you can decrease health points of 2 monsters by 1. So this would be down to 0 and it dies. This would be down to 1 and it survives. You need to minimize the number of seconds to kill all the monsters. And here, like, if you want to decrease 2 monsters by 1 and they will both survive, so they will both have positive health points, it doesn't make too much sense to attack them like that and then to, let's say, attack them again, because as well you can just kill them one by one. So this problem certainly was meant to be easy, where we should one-shot kill all the monsters with health points at least 2. And for those remaining ones where the health points is equal to 1, we can just count it, and those we can kill in pairs. If, for example, if you have, let's say, 20 monsters with 2+ health points, and then, I know, 7 monsters with only 1 health points, then you need 20 seconds to kill those monsters, and the remaining 7 you need to kill 2 at a time. And for that you need, in this case, 4 seconds. It will be 7 divided by 2, rounded up. And that's what I have in code. We n times read the health points, x. If x is equal to 1, then increase single by 1, otherwise this means those with health points at least 2. So we count single health point monsters and others. And the answer is the number of big monsters plus single divided by 2 rounded up. And by the way, whenever you want to compute a divided by 2 rounded up, the way to do this is a plus b minus 1 divided by b. This formula uses only integers to compute ceiling of a divided by b. And it's very useful. Of course, dividing by 2 is even easier. You can resolve that with an if. What I don't recommend is function ceiling. ceil function works using floating values, so doubles or whatever, non-integers, and generally you should use integers if possible. Non-integers have precision issues. Yeah, you can do some tricks like what Prebix says, but I don't think it translates well to other divisions. So I always use something that works generally for A divided by B. Or this same thing. Oh, I see. What this new suggestion with A modulo B not 0 actually always works, so that's nice. Maybe slightly slower. If you do division and modulo, both those operations are quite slow. So using this, A plus B minus 1 divided by B is faster, if ever the runtime matters. Here it didn't matter, and it's very small. N is, the sum of n is 20,000, whatever. It gets optimized in the same division, but was it the same division? I mean, I understand that it can be optimized. I'm referring to this. If it can be, if it's optimized, then indeed it's same thing. Because C++, when it computes division and modulo, it actually does some algorithm that computes that pair, and it will just give you one of those elements, I think. So if compiler is smart enough, then indeed it will not be slower. Cool, thanks. And I think let's move on to problem B. Stand-up comedian. We have jokes of four types. Why is it not aligned? Jokes of four types, and we need to say how many jokes in total we can use before we die, whatever dying means. B. Now, there are two people initially with 0 HP. So Alice is equal to 0 and Bob is equal to 0. And you have jokes, or let's say spells, of four types. There are jokes of type +1/+1, jokes of type +1 -1, -1 +1, and finally -1 -1. Those values describe how they affect Alice and how they affect Bob. And you cannot allow any of them. Maybe I will go full screen. You cannot allow any of them to go below 0. In particular, the first joke or spell that you want to use is certainly this one, +1/+1. So this needs to be first, otherwise you immediately die. You don't want any of those two values to go below 0. The question is, given the count of those four types of spells, you're given four values, each of them, the count is up to 10 to 8th power, I think. Usually it is up to 9th power, but then the total number would exceed int. You would need long, organizers apparently didn't want that. So we are given those four counts, call them C1, C2, C4, C3, C4. And you need to say how many jokes in total, or spells, you can use. In particular, if this first number is 0, this is a special case where we cannot use any spell. I will assume that joke is equal to spell. It's, I think, more common to think about such things with modifiers as spells. Actually, you're allowed to then use a single spell, but then the game is over. So the actual question is how many spells you can use. If when somebody goes below 0 here with their HP, then you need to finish. Okay, we want to leave them above 0. So first we will use all the C1. So this goes first. Then Alice and Bob are on some level. Maybe they are both on level, let's say 5, because there are 5 jokes or spells of this first type. And now let's consider how many jokes we can use of those two types. Obviously, the C4 type, the fourth type of jokes, is the worst because it decreases both, so it's only better to leave that for later. If you look at a sequence of spells or jokes that you use, it doesn't make any sense to move this before something else because you're only making it easier to lose earlier. And how I did it. I see that somebody is describing their solution. I'm sure there are different approaches. I will describe mine. So after Alice and Bob, they have some current health points. It tells me how much of C2 or C3 I can use, but also I can use them interchangeably. So if I use second type and then third type, in total that cancels out. So the minimum of C2 and C3 I can just use without any negative consequences or positive consequences. It just added. For example, let's say that this count is 8 and this count is 12 or 11. Then I know that here I will use 8 and 8 of both types, and then I decrease those values to 0 and 3 because I use 8 and 8. This is possible as long as those health points of Alice and Bob are positive. So Alice and Bob health points need to be at least 1. If that's the case, then I'm allowed to do this trick with the minimum of C2, C3. Once that's done, now I want to use the remaining amounts, which is in this case 0 and 3. And here I'm just limited by the health points of Alice and Bob right now. If Alice has 5 health points and I have 3 spells of this type, well, I can use all of them. I can use at most 5 spells. If Alice has 5 health points, I can at most 5 times do -1 to her health points. So what shapes so far is this. Answer becomes C1. Then assuming that C1 is greater or equal 1, so if we created at least 1 health point for Alice and Bob, then we take the minimum of C2, the temporary variable is minimum of C2, C3, subtract this, and answer you can increase by 2 times TMP, because TMP is how many times you use a pair of spells, C2, C3. So there's this part, and then for both C2 and C3 you look at how many times you can use this, and the how many times is minimum of C2 and the current health points of Alice and Bob, like that, and then minimum of C3, C1. For example, here Alice has 5 health points because C1 was 5. Then you're looking at this value, the C2 value, how many jokes of this type there are. Sorry, this is maybe this type, because this one decreases Alice. At most 5. The minimum of those two values, in this case 3 and 5, is how many times you should use this thing. You should increase the answer by that, and if you want you can update health points for Alice and Bob. After doing this, finally you have C4, the last type, which decreases both, and when, for let's say Alice is 2 and Bob is 4, how many times can we use -1 spell? Well, 2 times. Here we have minimum of Alice health point and Bob health point. For that, apparently we need to maintain them. And that's it, a series of cases, which we can see in code here. I will also talk about details related to that last spell to use. In task B, we start with answer equal to the first number, the number of jokes of the type that give both of them a health point. Then if A is greater than 0, I take minimum of C2, C3, so 2 other values, because I will just use them interchangeably, and I update that. I maintain apparently, I don't maintain, what do I do next? I do the minima, so if I know that Alice has 5 health points and I can use a spell that hurts Alice 7 times, then minimum of that is 5. This is how many times I can actually use the spell. I use that. And apparently in my code I didn't maintain the health points of Alice and Bob, I just knew what they are at the end. D is the number of existing spells of the last type, and I minimize that with health points of Alice and health points of Bob. And that's how many times Alice got cured with +1 in the first phase of our algorithm, minus then how many times she lost 1 health point. Then we increase answer by that. Finally, after all of that, I computed how many spells I can use without dying, but it is allowed to use +1 spell because you can use the final spell to go below 0, as long as there exists 1 more spell. So at the very beginning, I computed the upper cap for the answer, which is the total number of spells. If in total we have 30 spells, and as the answer here I computed that all 30 spells can be used to and without dying, then I output 30 as the answer. Otherwise I output answer +1. So the answer +1 is minimized with the number of spells in the game. Whether it's a lot of cases, I don't know. There are those 4 types, so it's difficult for me to imagine a solution that doesn't go through them in some way. I'm sure there are solutions that are shorter in terms of the number of lines, but it should be similar anyway. And if constraints were lower, if it wasn't 10 to 8th power and instead constraints were up to 100, then maybe you could greedily make choices about what spell to use. You should say then that first we use spells of type 1, then we greedily use type 2 and type 3 whenever possible, whenever something doesn't lead to dying, to going below 0, and then type 4. But from the very beginning, because constraints were so big, 10 to 8, we cannot do that. Should Bob and Alice be the same after we add that? Yes. I mean, we don't update their health points. I'm saying here that if what happened here is this: if 5 times you can use -1 +1, and 7 times you can use +1 -1, then what I'm doing is I'm using this 5 times and this 5 times, and this completely cancels out, so it doesn't affect their health points. And here I multiply by 2 because I'm using 5 times this type of spell, 5 times that other type of spell, so in total 10. This is the count that I use for both type 2 and type 3. For lower constraints, this thing can still be applied. What I was saying is that for lower constraints, there could be a different solution and maybe easier solution without such cases and computing minimum and checking that. We could approach this more greedily. Also, maybe there is just a formula that solves this, but what I came up with is this. Moving on. C, permutation. That's the first tricky problem, something that I perfectly understand somebody not coming up with a solution here. It took me more than a few seconds to come up. What do we have here? We have a sequence, like 1, 5, maybe without commas. 1, 5, 4, 2, 3, and we want to sort it. What we can do in one move is we can choose 2 numbers, let's say 5 and 2, and we move smaller number to the beginning of the sequence and bigger number to the end of the sequence. That's our move. Then we maybe want to repeat that. I will move 1, I will choose 1, and I will choose, let's say, 3. I will show a case where this doesn't work. 3 will be moved to the end because it's bigger, 1 moves to the beginning. And you continue doing so. Here, this wasn't optimal. What we should have done instead at this point is move 1 to the beginning and 4 to the end, but earlier than 5. So right now this wouldn't work, but it's almost there. 1, 2, 3, 5, 4. We didn't succeed. So clearly 5 we should move at the end. Let's try that again. We have a sequence 1, 5, 4, 2, 3. I should keep choosing two numbers and moving them. Now, choosing 5 at the beginning is stupid, because if I now move 5 to the end, later some other number will move there, and I will waste a move. I will need to move 5 again. So 5 should stay for later. What I should choose here is numbers 2 and 4. Those are not the smallest, not the biggest. If 4 moves to the end and 2 moves to the beginning, then thanks to that now we can win in one move. We can choose 1, 5. 1 is smaller, so moves at the beginning. 5 is bigger, so it moves to the end. In the last move, it makes sense to take 1 and n, and they will move to proper positions. So the second last move should take 2 and n minus 1. Third last move should take 3 and n minus 2. Here, the easiest thing to decide is what should be our last move, because in the last move you will move something to the end of the sequence, and that must be n, because n needs to be at the end. And 1 similarly at the beginning. So you can move backwards like that. The question here is, how many moves do we need to sort the sequence? So, and I would here work backwards. If the last move is 1n, is that enough to solve the sequence? Let's see an example where this move is enough. If the sequence is, let's say, 5, 2, 3, 1, 4. For such a sequence, if you just focus on moving 5 and 1, then everything will become sorted. And that's because the remaining elements are already in proper order. 2, 3, 4 are sorted relatively, so moving 1 and n to the outsides is enough. So one possible approach is move backwards here through the moves, like knowing that the last move should be this, and always check if the remaining elements, so everything except for 1n, then everything except for 1, 2, n minus 1n, and so on, whether they are on proper positions. Like if this fails, not proper positions, if they are in proper relative order. For example, let's say, this is task C. Let's say that n is equal to 10. Moving backwards through moves and knowing that the last move should move 1 and 10, and the second last move should move 2 and 9, you're basically asking if numbers 3, 4, 5, 6, 7, 8, if they are relatively to each other properly sorted, and you don't care where are numbers, let's say 1, 2, 9, 10. You don't care about those because you will put them out, and you will put it at the beginning and at the end. So how can we efficiently do that? Well, because we will need to know if some numbers are relatively, like if one number is on the left from the other, it helps a lot to create an array, a helper array, where every number is. Let's say like that. For every value, I want to immediately know what is the position where it is in the initial sequence. It's easy to create such an array. It's often, this might be called inverse, because not for every index normally you know what is the value, and here for every value I want to know the index. And then one approach, I guess, would be for various values to know if the next value is more to the right. So solution, I didn't go with that solution, but let's say solution 1 is for every value x, check if it's if x plus 1 is to the right, and report that thing as 0 or 1. And then if you know it for every value, So we have values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the input, they are in different order, of course, but imagine numbers from 1 to 10. For each of them, you check that using the array I've just described, and you just write down 0 or 1. Let's say this 1, 0, 1, 1, 1, 0, 0, 1. This 1 means that, or true, it means that 6 is on the left from 7 in the original sequence. So this thing might correspond to the input like maybe 3, 4, 1, I'm trying to think, 5, 2, 6, and some other stuff. This would be the beginning of the input. And for every number, for 1, I checked if it's to the left from 2. Yes, it is, so I'm putting 0. For 2, I checked if it's on the left from 3. No, that's not the case, so I'm putting 0. And so on. 3 is on the left from 4, 4 is on the left from 5, and so on. I will care a lot about those numbers being in proper ordering, 3, 4, 6. And here what I need to check, to know if numbers from 3 to 8 are sorted, I check if everything here we have ones. And there are different ways to do it. For example, you can do prefix sums, but it's an overkill. If you think about it, this can be done much easier. If you go like from the, when you consider first moving 1 and 10, you just get rid of those two elements. So it's like 2 pointers, but easier. The problem, the problem boils down to this. We compute the sum of all those elements, or the number of zeros, and you move from the beginning and from the end with the same speed, and you check when you get rid of all the zeros. This can be done. And this is one solution. You can later think about it more and analyze that. But I will show you in my code is different. And that's moving from the middle rather than from the endpoints. We want to know, I here said that we can move backwards, but actually I know that if I keep moving backwards, eventually I will be left with a number 3. Number 3 is in the middle, and surrounding it are 2, 4, and then 1, 5. If this is the original sequence, eventually what I want to get is 3, and then 2, 4, 1, 5. 3 is the very middle element. For if the length is even, then 2 elements are in the middle. 3, of course, is properly sorted, and then I can just check if numbers 2 and 4 are sorted as well. So what I did in my code is I created 2 variables, L and R, initially both equal to 3, initially both equal to the middle. And then I keep checking if I can expand this. I check if numbers, if I move L by 1 to the left and R by 1 to the right, let me hide myself for a moment. If I move right by 1 to the right, will this range still be sorted? So let's say that this is solution number 2. Let's say that I know that in the total sequence, numbers 2, 3, and 4 are properly sorted. I already know that, and I don't need to touch them. Then what I will check next is I will check where is value 1, I will check where is value 5, and I will verify that they are properly sorted with their neighbors, with 2 and 4. So if this a moment ago was LR, I will check the following. Check if where of L minus 1 is smaller than where of L. As I told you, this checks where of X will tell you where is value X, what is its position. And where of R is smaller than where of R plus 1. If both those conditions are true, then you can decrease L by 1, increase R by 1. And you keep doing this as long as this is true and you are not out of the values. And at the end, you will get, you will know what are values that you do not need to touch. If, for example, 2, 3, 4 are relatively sorted, where 3 was the middle element, like n over 2 or so, then you know those don't need to be touched, and you just want to know what is the number of remaining elements, and this divided by 2 is the answer. It's not longest increasing subsequence because the middle is very important. The last move was 1n, the second last move was 2n minus 1, and so on. Like nothing else makes sense if you think about it. Maybe let's think about it like that. If you realize that in the full sequence there is a long increasing subsequence like that, this doesn't help, and you cannot say that you will just move those other elements. Like this is out of place and this is out of place. If this is the input, you cannot solve it in one operation. Because if you choose 6 and 5, which are both bad, they are in wrong positions, well, you don't have a choice of where they go. Smaller one will go to the beginning, and bigger one will go to the end. So 5 will break the beginning. The last, if you want to solve it in one move, you need to choose 6 and 1. That's the only choice. So you're checking if values from 2 to n minus 1 are good. Okay, and now the code for C. As I told you, I created the inverse array of where everything is. For every value, I know its position. I kept indexing 1 through n, as the statement mentioned. I didn't use 0 through n minus 1. There is a special case of n equal to 1, because then I realized that something with my indices wouldn't work later. And what I choose first is the 2 middle elements. I here spent a few seconds during a contest to decide the exact indices. My logic was this. If n is equal to 5, I want both middle elements to start as 3. If n is equal to 6, then there are 2 middle elements, and I want L to be 3 and R to be 4. And given this target, I just figured out proper formulas. Obviously, it should be around n over 2. But if you choose n over 2, it will not work here. For n equal to 5, I want to say middle element is 3. So apparently, at least I need to round it up. If I both just round up like that, the formula for even n will not work. So the other value increased even more. I rounded it up again. This certainly wasn't necessary, figuring such formulas. You could go with ifs. I'm sure that you can do if n modulo 2 is equal to 0, L is equal maybe n over 2, R is equal L plus 1. Something like that. But I just could figure out formulas that work in both ways. And certainly the remaining logic I didn't want to repeat for even and odd case. Okay. Oh, I see. I decided here that by default, if I don't see anything that I can not touch, then the answer is the number of elements divided by 2 rounded up. So this is the default answer if I decide to move every element once, if I just pair them up. And then there's here this complicated while. Mainly it's what I told you. So it checks if L, I think I told you that I should compare L with L minus 1 and R with R plus 1. Here I'm looking backwards towards the middle. I'm checking if L and R are good. So those are, I think, I'm not yet sure if range L to R is good. Is maybe good, I will say, maybe here is crucial. And I'm checking if range from L to R is good, and for that I check if L is to the left from its right neighbor, L plus 1, and R is to the right from its left neighbor. For example, if n is equal to 6, and I take L is 3, R is 4, this will already check if 3 and 4 are relatively in good positions. 3 needs to be to the left from 4. Apparently I also added that because if we have the odd case and L is equal to R, so it's like one element, then automatically it is good. So I say, if it's just one element, then it's properly positioned. And if that happens, then also it's good. L greater or equal 1 prevents me from going out of bounds. So I check that stuff, and if all of this is true, I decrease answer by 1 because I know this is a pair that I'm saving. I don't need to do anything for that pair. And I move L and R. I can take a look at some example. This thing, I will then copy it and analyze. Let's see. If I move 1 and 2 and 9 and 10, then everything else 3, 4, 5, 6, 7, 8 is properly positioned. So yes, the answer should be 2 for that case. I don't know why you're asking exactly, but the code I think should behave properly. It will start by checking if 5, 6 are in good positions. Then it will check if 4 and 7 is good. Yes, it is. 4 is on the left from 5, 7 is on the right from 6, then 3, 8, and then 2, 9 will not work, so it will stop at 3, 8. Do you want me to run my code for that? I should first specify the number of test cases and the sequence. Yeah, it printed 2, like expected. Why are we going from middle? Why it can be any other position like that? 5, 4, 1, 6, 2, 3. So what do you want to do here? Maybe this. If you have doubts about why I'm going from the middle, then figure out, create a test with answer equal to 1. I think that's a good idea. So create such a test where you see that one move is enough to win. And then by trying to do that, you should realize that the only possibility for that is that this is equivalent, that numbers from 2 up to n-1 are sorted. There is no other way. Try to create a test with this answer where this is not true or something else is true, and you think that that's more important. Okay, that's, I think, everything about C. Before we move on, let me take a look at whether there is an editorial. I don't think so. I will later read this. It was difficult. Okay. Is there any name for this type of sorting method? I don't think so. So this wasn't really... there are a lot of problems where they are describing a particular type of operation, but it's always very artificial. It's not meant to, exist in real life. It just, if we consider this strange scenario where we are only allowed those operations, then what happens? Let's go into D, fixed prefix permutations. This one I would say had similar difficulty to the previous problem. I don't know. Well, that's a reasonable gap, but E is significantly more difficult. Let's see that. D. We were given some condition. We have a lot of permutations, all of them of length 10, which was very important. I first didn't notice that condition, and still the statement looked reasonable. And I just went into ideas like hashing. For every permutation, so let's say, let's look at permutation number 1. Permutation number 1 is something, let's say 2, 4, 1, 3. I'm just rewriting it from the first test. I want to find another permutation, some kind of PJ, such that, if possible, we maximize something, but if possible, let me see, this is defined, Pj of P1 of 1 is equal to 1. That's the condition. But I'm already looking at particular permutation, so let me just, I know what this is 2. So there is a requirement that this other permutation should, at the second position, have number 1, which means the following. Every other permutation you can imagine as 4 underscores. Generally, at least for me, it's easy to think about sequences as underscores whenever you don't know the full sequence. I recommend that approach. Next time, please stream on YouTube. I am streaming on YouTube. So you can find the link here. So we want, because first number is 2, I want number 1 here. This number is, next we have 4, which means on the 4th slot, I want number 2. And at every step, after filling a new number, I wonder, is there another permutation in the input that matches this description? If so, I move on. Number 1 on the 3rd slot. You might notice, by the way, that what we're creating is the where array of P1. So this is the inverse array. Let's take a look at a bigger example. Let's say that P1 is, I don't know, 4, 1, 5, 6, 2, 3. Then I'm looking for a permutation of length 6. If possible, on the 4th slot it should have number 1. On the 2nd slot it should have number, wait, 4th, yeah. On the in the 1st slot it should have number 2, and so on, because those are just indices. 1, 2, 3, 4, 5, 6. And so yeah, on the 1st slot number 1, 4th slot number 1, index 1 number 2, index 5 number 3, and so on. You can keep filling that. 6, 4. And you wonder how long something like that exists. How long there is another permutation that matches that. You don't have enough time here to iterate all the other permutations. The brute force here would be n squared times something. I think m, or doesn't even matter. But n squared is too big. If always for every permutation P1 you iterate other permutations to try to find something. You cannot do that. So no, that's not the way to go. And there is a way to directly do it and ask a question like, is there something with this pattern? And we can for that use hashing and optionally subsets or masks. And that was my first idea, that for every permutation as preprocessing, I will iterate its subsets. And like, you know, when I see a permutation, like let's say 1, 5, 3, 4, 2, 6, I will consider all possibilities of replacing some subset of elements with 0. Then I will compute the hash of it. And I will say that whenever I'm looking for a pattern, I get the hash and I check if this hash exists. And later I realized that's unnecessary. That being said, if you're on the level of solving problems D in Division 2, you should know such a technique, I think, at this point. Anyway, what is enough, because this goes in an easier order. First of all, we don't need hashing, and instead, for every other permutation, what I need to do as preprocessing is I need to just replace everything except for a 1 with zeros, and then here there is a 1, and this I need to put into something like a set. Then wherever there is 2, I also put this into a set, and so on, continue. So for example, if in the input there is a sequence 1, 2, 4, 3, then I made the following, that's too easy, 2, 1, 2, 3, 1, 4. Then I create few arrays out of this, 0, 0, 1, 0. This is an array where only number 1 is activated. Now I activate, so I turn on number 2, number 3, number 4, and all of them I insert into some kind of a set. And I will have a set of vectors with all those possibilities. Now, for every permutation, when I keep considering every number and turning it on, I will check in that set if that exists. And this will be my solution number 1. So solution 1, again different than what I implemented, is this. First phase preprocessing. For everything you want to prepare that maybe this permutation will be needed to some other permutation as this bit mask. So maybe if I am 2314, maybe some other permutation will want to see 1 on the third slot, and then it will want to see 2 on the first slot, and so on. So what I do is, for example, you can again create that inverse array where, as I've described, then you create, for every permutation, you create something filled with zeros. You create a vector filled with zeros. And for every value x from 1 to n, you turn that thing on. This means from 0, wherever x is, I turn that into x. This will turn everything on in proper order, and after turning it on, set insert v. That is fast enough because lengths are small, so the time complexity is O of n times something small. We don't really need to analyze that exactly because n is small enough. And as part 2 is the actual solution for every permutation. I look at every consecutive number, and this tells me where something should be. So for every permutation, I create again n zeros, or n plus 1 zeros. I see a question here. Do you have any idea for bigger m? Yeah, I think that's as long as we can do it in O of input times logarithms using hashing. I don't think that's impossible. I will take a look later. So we do this, and then for every, this time more like position, let's say they are numbered from 1, if I see something there, so in the input I see p of I, this number is first on the first slot, then second, I know that on that slot there should be I, and I check if set contains v. If so, I keep moving on, so I answer plus plus, else break. Because we want as many as possible initial numbers to fit. And this will compute the answer for every permutation. Well, won't it be out of memory? No, m is small. I didn't compute it exactly during a contest, but I'm expecting something like for every permutation, m times I insert a vector of size m to a set. So this is memory. This is space complexity. The time complexity is the same multiplied by logarithm if we want to use sets. Okay, that was solution number 1. Solution number 2 is what I implemented, and it's slightly different because I think it's slightly different. But it's like the other way around. Instead of from one permutation looking at the second permutation, for second I looked at the first one. I don't now remember exactly the differences. Oh, I know. If we see a permutation that looks like, let's say, 2, 3, 4, 1, for every value, I see where that is. So first, let's say p equal to 1. I find that it is on position 4, and then to the prefix I push back 4. So I create an array with just one element, a 4, because 1 is on the 4th position. Then I add, where's 2? Here, 1. Then I add, again I push back, where is this one? And where is the last one? So what I add is for every next value, 1, 2, 3, 4, I push back its index as this kind of prefix. And this will tell me what other permutation would want me. This says, if another permutation starts with 4, 1, then it will be happy with me as this candidate other permutation. If something starts with 4, 1, 2, then it will be happy with me. There will be a match of size 3. So what I insert to that set is those vectors of size from 1 to n. Not all vectors are of full length n. I create those prefixes, and then I iterate again for all the permutations. I just take its prefix. First I take first element, then with second element, and so on, and for every prefix I check if this exists in my set. If so, I move on, otherwise I stop. That's my solution. It's the same, just looking at like from first to second permutation instead of second to first. Yeah, the title is messed up. Yes, there was some issue, I think, with cast or something, where the stream on YouTube lasted 3 seconds and then it stopped. Then automatically it moved to the stream from yesterday, which is bad, of course. I fixed the title now. Okay, and that was task D. We're 1 hour in, roughly what I expected. As I told you, I didn't think much about F, but I tried E, and it's embarrassing, but I couldn't solve it in, say, half an hour. But there is a description here, so let's go through that together. I mean, I coded something for E, but then realized some issues with that. I actually had 2 very different ideas, both didn't work. So let's see, for E, this is the description. Generate all divisors, I did that. And for every divisor, instead of the minimum row where it appears, let's search for the maximum column. Find its maximum divisor, which is not greater than n. Oh, I see. Well, that's very easy for me to fix in my code. So in like, I don't know, 3 minutes or so, I'm able to do it. That's a nice idea. Then actually, after reading this, I can discuss the solution, which is lucky. Okay, so solution for E. I didn't got that, but I understand. Problem E. We are given few values. One is n is up to 1 billion, and also there is some kind of m which is up to 10 to 18th power, which is given in some format of a product of 2 numbers. Long story short, we can factorize that. We are able to factorize this fast enough, and we will do something with divisors of m. Divisors of m. Now, there is this claim that is not true in math in general, but in competitive programming is very easy, is very useful. The number of divisors of a number can be estimated, it's not really correct, as cubic root of m, m to the power 1/3. You should remember that and always use it. So, number up to 10 to 18th power only can be up to 1 million. It's not the exact value, but it's good enough. Number up to, I don't know, 5,000, I claim will have around 20 divisors at most, as an estimate. You cannot say that in a computer science exam, but you can use that, and you should use that in competitive programming. I'm not saying that in that time complexity you can find the divisors. Finding divisors of such a big number normally is difficult. You need Pollard's law for that. Here it's easier because of the format. So step 1 is to actually find the divisors. Step 2, well, I didn't say what n is. We consider a multiplication table n by n. Like here, this is multiplication table 6 by 6, going up to 36. And for every divisor of m, and there are, let's say, 1 million of them, we want to say what is the first row where this number appears. So if, let's say, 15 is divisor of m, then we see that in this multiplication table 15 is here, and we report, yeah, that's row number 3. We need to print something like the sum of all the answers, but just for every divisor, you need to find this first row where it appears, or 0 if it doesn't appear at all. Mohs algorithm. What I mentioned before is Pollard's law. This is faster factorization, but it's not needed. Okay, now if you focus on that, finding the first row, that's bad. Okay, so maybe first, how do we find divisors? M was given in the format m1 times m2. You could find with brute force, in square root time complexity, you can find all divisors of m1, find all divisors of m2, and pair them up. If you know that 70 is divisor of m1 and 5 is divisor of m2, you can consider 350 as divisor of everything. And you create, I know, a set of those divisors. So first step, find all the divisors. Okay, that's done. And then we change the problem a little bit. By default, the problem is that for every divisor d, find lowest row such that, so smallest, such that, what's that? D modulo row is 0, so d is divisible by row, and d divided by row is smaller or equal n. Because they say this needs to fit in the multiplication table. For example, 15 is in the third row, because 15 is divisible by 3, and 15 divided by 3 is 5, which fits in the table. So you require both of those, and it turns out that it's very easy to do that. But instead of minimizing the row, we will maximize the column where we find that number, and then we can say that we just maximize the column, and column is smaller or equal n, and that will be for some reason easier. For the reason that like if you think about this problem for longer than 5 minutes, you will try to, like when you, let's say for number 15, you decided where it is, you will want to use it to see where 30 is. You don't want to compute it independently for every divisor. You want to do something like dp on them. And with that definition from a moment ago, it was impossible. Here, it will be possible. Because if number 15 is, let's say, is in column 5, then we know that number 30 is also in column 5. It might be in other columns as well, but it will be here. And the row where it is of course twice bigger. But the column is that, and I kind of don't care about the row. In this, I never have a condition for row. Possibly row is bigger than n, but then I will just print 0. I want to find this maximum column. I don't care about the row. So by that, maybe it's a good observation to say this. We pretend that the grid is now infinite going down. It has infinite number of rows. This doesn't affect the answer, because you can safely assume that this multiplication table has infinitely many rows, and then if for every number you find the first row where it appears, it's enough to say what should the actual answer be. So maybe this mental hack, infinitely many rows. And thanks to that, we can say that if 15 is in column 5, 30 is in column 5 as well, just twice lower, and the grid is, let's say, infinite down. Of course, every row is still limited by n. And thanks to that, we have the following easy DP, where when you want to find DP of 30, so you want to know number 30 is in what column, you will say that this is maximum out of DP of 15, DP of 10, and just all the divisors, and DP of 6, and that's it. On purpose, I only wrote those divisors. Why is that? It's clear that for each of those numbers, if this number is in such a column, then also I am in this column, because I am a multiple. Like, look here, number 6 is here, so 12 is also here, 18 is here, 24 will be there, and so on. And why am I only considering this? Because when you do DP on divisors of some number, they create this more complicated structure where you don't need to do all the transitions. For example, divisors of 100. There is 100. 100 has a divisor of 50 and also 20. 50 has 25, 10. This has 4. And you can continue a little bit here. 5, 2, 1. And this structure that you can get by only for every number multiplying or dividing it by a prime. If you divide 50 by 5, you will get 10. If you then divide 10 by 2, you will get 5. In DP, you only need to consider those direct transitions and everything will be propagated automatically. This is very common. Where can I learn the hashing technique that I mentioned? Yeah, if somebody in the chat knows a good source, you can provide that. Generally, you need to know hashing and you need to know how to iterate subsets of a sequence. I don't know a source exactly for that. Okay, so now in code, I will now do that in code. I already have most of the stuff that is needed, because I'm finding all the divisors. And then I want to create a map, because divisors are long. So yeah, a map with the DP. Initially it's empty. And for every divisor, I want to compute it by, so if for example D is 30, I want to consider 15, 10, and 6, which are numbers of form this divisor divided by a prime. So for all the primes that are among divisors, if D modulo P is 0, dp of D maximize with dp of D divided by P. And also, this way you find maximum column. Also, if what we are doing. If d is smaller or equal n, then dp of d is d. This means that this number actually fits in the first row. Print dp of d. And everything here that I used is unnecessary. Let's run that. I need the input. No, minimize, no, because I turned the problem into maximizing the column. And here I need to print that, because this is the maximum column, and now I will get the row. It's suspicious that there aren't any zeros here. So I'm doing something wrong. Maybe before dividing, let's just print this directly. Also, I had something very similar to this in my code. I just didn't have that mental transition from rows to columns. Okay, I think that this is okay. It's just that answer here is dp of d, or no, it's d divided by dp d. So I switch between row and column. And if answer is smaller or equal n, or if it's greater than n, then becomes 0. And now let's print it. Does that match? 0, 3, a lot of zeros, yes, and here it matches. Cool. What's left is, because this output would be big, they said that we need to print the XOR of everything. So total XOR, XOR with ans. XOR also is some kind of hashing. Two, 0, and 5. 2, 0, 5, that's correct. I also need to print the number of non-zeros. Positive. Like, while solving this problem, you should ignore the fact that the output is strange. Positive, not posivit. This works, and I wonder if we can submit. If I get here wrong answer, then I'm guessing it will be because of overflows. If time limit exceeded, then I will start actually caring about efficiency, and maybe I will replace set with something faster. Time limit exceeded. Well, it shouldn't be very difficult to test, to find the max test locally, that being said, because you just need to find a number with a lot of divisors, and that should be pessimistic. And this is apparently such a case. So let's just check. Am I doing something in a slow way? I wonder. 2 seconds. I want to investigate which part is that slow. Let's stop here. Blazing fast. Stop here. Blazing fast. Primes. Set of primes. Maybe to verify what is primes.size. It should be very slow, very low. 22. And why did everything become fast now? Maybe I compiled differently. Yes. Okay. With proper compilation flags, and Codeforces also uses them, It's like production versus debug flags. It's 0.4. Multiplied by 10 tests, it's 4 seconds. So I just need to speed this up a little bit. And for that, I need to avoid using dp so often. So I will here say this, and I will keep referring to me. I used reference to the map, so only once map is used, and every other time I will use me, which should make things twice faster, because this is a bottleneck, and I'm not reusing this every time. Maybe 3 times faster, because now only once I access a map. A moment ago I accessed that 3 times. I think it's int. It got 2 times faster. Should I speed up anything else? Let's submit this. I mean, my computer is usually faster than Codeforces, so I might again just get time limit exceeded. I wonder if this test was part of pre-tests. So would I see that time limit exceeded during a round? Okay, pass that test. That's 98% of the time limit. Perfect. I would be able to squeeze this more. Just generally map is slow. Instead of that, it would be better to use a vector. I even implemented that for some other reason. You can use a vector. Every new DP I would here push to a vector, and you would then binary search some old number to get the index of it in the vector. And then I estimate it would be like 6 times faster. Space complexity isn't the issue. Time complexity is. Use Python map. That's a way to get time limit exceeded. Okay, this is a better idea. Use hash table. Yes, it would be faster, especially that fast GP hash table. A summary of the solution, and then I'm finishing the stream. We wanted in a grid n by n to find every number. Like we are given number m, let's say m is 100. In a grid, let's say 7 by 7 of multiplication table, I want to find every divisor of m. And if it exists in multiple places, I want to find the first row where it exists. So divisors of 100 are, for example, 25, 50, 4, 10. For each of them, I want to see, even if it appears in multiple places, I want to say, well, this is the first place, that's row number 2, so I'm adding 2 to the answer. And this is task E, by the way. So I will put it here. This is task E, so it would be easier later to watch. Now, instead of finding the first first trick is we assume that there are infinitely many rows. This doesn't affect the answer much. There is still limit for width, but here there is just infinitely many rows. If at the end I will realize that some answer is that for the first time it appears in row number 50, okay, 50 is greater than 7, so I will just replace that with 0. That will be the final step. Second trick, instead of finding the first row, find last column up to 7 where it exists. When one number is in multiple places, always smaller row means bigger column, because you're representing 10 as 2 times 5 or representing it as 5 times 2. Obviously, when first number is bigger, then second number is smaller. And now we are going with this, which find the last column. Of course, this cannot exceed n, cannot exceed this 7. And with that, now we go for divisors of m. They are not difficult to find. And for every next divisor, 1, 2, 4, 5 in increasing order, we find the answer. Let's say we are now looking at 20 and we want to know what is the last column where 20 appears. First, we consider that maybe it appears in the first row, and that's a special case. But otherwise, I look up simple divisors of 20. And simple divisors of 20 are 10 and 4. Only those. I check what is dp of 10 and dp of 4. And I realize, so the last column where 10 is here, and the last column where 4 is here. So I consider that, and I say my answer is maximum of those two values. Why do I consider only those instead of other divisors of mine, like 5? Why don't I consider that? Because 10 considered 5. If 5 was in some column, let's say 5 was here, then also 10 will be somewhere here, and 10 already knows that it can be there. And this is very common. Whenever we do dynamic programming on numbers that are divisors of each other, almost always for every number we only consider its basic divisors. Can we use unordered map? Yes, we can. I try to avoid that because unordered map sometimes is faster and sometimes slower than a map. What we should use is gp hash table map, this thing, because it is just faster. Okay. That's everything today. If you want to see my code, see my submissions, then you can just find me on Codeforces and go through my submissions from today. And if you have some questions for those problems, I think still Codeforces blog is the best place to discuss that. If you have questions about my codes, then maybe leave that in YouTube comments. Otherwise, just use this blog on Codeforces for discussion. That's the main place. Thank you everybody for watching then. And I think see you next time this week. I will do the goodbye round of 2022.